All right, good, because I'll have you teach after the next few slides.
I didn't actually figure it out. I think
Okay, here we go. Not a chance. Now that Seth's here, we can start.
Hey, Seth, I like your shoes. You're not wearing your yellow man.
There we go. Okay, apparently we were here. We'll do the math in a minute, but we should run out of any new slides here in like a few slides. That many. Well, there's more than I guess I thought, but we'll be fine. So here we go, my friends. We ended on diffusion, which is the ability of a substance to penetrate into the gas or liquid environment of another substance or whatever. So you go from a high concentration to low concentration. You've learned about it forever. The smaller something is, the faster it fuses and diffuses because it's moving faster. So I don't know, not too hard. That's what we talked about, like smelly lotion. And we wished Alyssa was here because she probably has smelly lotion. But whatever. You okay with that? Okay, real gases. We've been talking about what type of gases this whole week and a half. Ideal. They are not real. They don't actually exist.
Yay.
Wait, what have we been learning? Is this like imaginary numbers and math?
No.
Is it like we're modeling something, but it won't ever happen that perfectly because the world is.
That's much more accurate. What we're saying, when you take physics, if you haven't already, they're gonna be like, a ball is flying through the air, ignore friction and air resistance. Yep. And that's not really how it works, but math's millions of times easier that way, right? So a real gas is how they really behave, but ideally they're pretty similar and close enough for all we care about. So we'll talk about real gases versus ideal, but we're still going to do the math of piv nert, which accounts for an ideal gas. That's why it's called the ideal gas law. But you do 100%, you need to know when an ideal gas is different significantly than a real gas. And it's not very hard. So in the real world, the behavior of gases only conforms to the ideal gas equation at relatively high temperature and low pressure. So real and ideal are pretty similar at high temperature and low pressure. So when would an ideal gas not conform? Just reverse them. High pressure and low temperature.
Oh, I get it.
And that really, we'll go over a few more slides, but that's ultimately what you need to know is when the behavior of a gas deviates from the ideal gas law. It's when it's cold and pressurized, which interestingly enough, if you take a gas and you make it cold and pressurize it, it turns into a what? A liquid. And a liquid doesn't behave like a gas. If it did, we'd call it a gas. So the more liquid-like or the colder and higher pressure you get, the less ideal it becomes. Easy enough? Now the ideal gas law goes to the K-Mott that we talked about before, the kinetic molecular theory. It says that there's no attraction between particles, that their collisions are inelastic. When they interact with the wall, they just bounce off. Once again, they're inelastic, and their volumes don't occupy any appreciable space. But as they get colder and more pressurized, it becomes more important. 1 second. We have HOSA. 3, 2, 1, here we go. All right. Jackson had a question.
Why is it when it's higher pressure? Because wouldn't that heat it up?
It may heat it up, but the higher the pressure, think about a piston here. As you push down, oh, it's all, hold on, it's together. This isn't going to work very well, but pretend as you push it down, yes, it heats up, but now there's hardly any space. So they're significantly closer. And if they're closer, then their natural attraction that they might have increases exponentially. Because it's really forcing them close together.
So the reason that like gases don't behave ideally is because the different parts of the molecules will have different charges, so it'll mess up.
Yep. we haven't learned about them, but there's these things called van der Waal forces, where everything is actually attracted to itself. Now, not very much on some things, and then a ton, like on your desk, highly attracted. Then the molecules in the air, not very attracted, but somewhat. And so we say that they don't, but they kind of do. And as you get closer and closer, the van der Waal forces start to interact, and then we form a liquid. And that's our next 2 chapters, is where we're headed. Oh, I didn't hear your joke. Yes.
Did I miss anyone else?
Anyone else want to bleed next week?
And then if you took a permission slip and you want to sign up, find these posters, and scan the QR code to get an appointment. I think there's one just outside here. So, thank you, you guys are awesome.
Do you know what this means?
I have a question for the blood donation. Just on the profile, it says EXT parentheses H. What is that?
I don't know. I made a profile and don't remember seeing that.
All right.
So, yeah, if you don't know what it is,
then.
don't fill it out. 'Cause, yeah,
It's not after your phone number, right?
It was after my phone number. Right?
That's like if you work in a company, like 3785, it's your extension.
I see.
You
I didn't know
don't-
that.
you don't need
I didn't know.
But I don't know why there's an H.
All right. They just wanted to throw it. I'm good. I'm good.
They just want to confuse you.
That's all right. You're welcome. That's back when people didn't have cell phones in their pockets every second. Used to have a home phone and a work phone, and they'd dial into the school and then have an extension. But now it's like, screw that, I'm just dialing his pocket. Yes, Seth. Hey, it's Purple Friday tomorrow. Don't let my man Seth down like you did last week.
Purple Friday. I'll wear a purple mask.
Thank you.
Purple on Friday.
It's because you always have a red jacket over the top of it. It's like me. I always have a shirt on under this, but I could wear the same shirt under this for 5 straight days.
And no one would know.
Because for 4 days in a row, I've had this gray light jacket pullover or a different light gray jacket pullover. Yeah, that's what I call it now. I pretty much wear the same exact outfit every day. I rotate out like which pair. You probably always think I wear the same pair of pants too, but I have 3 of the exact same pair of pants. Like 100% exact same pair of pants.
My mom did that. She just bought me
How
like.
do you know that you're not wearing the same pants?
I rotate them on my hooks.
How do you know that you do that successfully? Now I'm messing up.
I don't, but it doesn't really matter. Like YOLO. Yeah. Okay, moving on. There's more. Here we go. So this will just sum up everything I just said.
Hi, everyone. Just letting you know we're about to have a fire.
I forgot. Hey, we're about to have a fire drill. No, just leave all your crap here. We go that way and we peaceably assemble, just like the Constitution says we can. Here's the deviations. We already said it. This is just backing up what I said. The assumptions made in kinetic molecular model break down at high pressure and low temperature. So that's where the model breaks down as it becomes closer to being a liquid. The ideal gas equation can be adjusted to take these deviations from ideal behavior into account. The corrected ideal gas equation is known as the van der Waals equation. You don't have to know it or calculate it. You just have to know it exists mostly. You used to, but it's this little piece right here. All right, so you have the pressure plus this factor times V minus this factor equals nRT. And what N, it's a square and B squared. You just were given these values of A and B, so moles, whatever, moles, whatever. It's just, it's there. You do not have to do this math at all, but it's the way that they adjust for how things change. Go ahead.
Why are there twos on the top and the bottom of that fraction? Why can't we just?
It's squared.
Oh.
He just said this.
It's okay.
Like, how much did it change?
Barely at all,
But it's more exact.
but it's more exact. And so like if you were at ATK or like Autoleave. Autoleave is extremely accurate with the gases their airbags produce for a reason. And that's because if they're wrong, you die. You either hit the steering wheel or the pillow's too hard and it breaks your neck. So like they are super, super exact. So they'll take into account the van der Waals equations, but they're like, they move it by like 100th or 1,000th. But their mass machines measuring to the 10,000 place. So it's important in industry and stuff like that, but definitely not in anything that we're that worried about. So I wouldn't stress too much about it. Sound good? Okay, just know that they exist. I drew that. Oreo Dan, that was for you. We cheered when you came in, so thank you. Yep. When we go to track meets, hold on.
Wait, is that a picture
I don't remember who this was, but yeah, the end. So, did you feel okay about the math problem yesterday?
Actually, I felt better than I did.
I figured it out. I did today.
I did not.
Part F?
Oh,
That's a bonus.
I did.
So like, if
Most
there's any
people do
leftovers,
the
like,
bonus,
we
but
could-
I think everyone.
if so.
It was this one, right?
Yeah.
Were the numbers exactly the same?
Yeah.
Okay, so we had done it a little bit before we cheated, but here we go. You were okay until F?
The bell rang. There was some technical difficulties at the start.
There was a lot of.
Someone's like yelling at everything. He's yelling at the computer and like, I don't know.
My mouse is extra fast. I forget. Old people struggle.
And then like I got on the wrong screen and it was just like.
It is tricky. That screen is not on, but you can accidentally drag something there and it's just dead. Only like 2 people in the world know how to get something off that. Just kidding. Me and one other person I can't tell you because if we both died, no one would know. So it's not hard. No. Look, does everyone know that you can grab a screen and take it all the way to the left and then it splits screens and you can select whatever program you want? That's how you get it back from the nether. It's not that bad. Okay. Here we go. Never mind. Derek's girlfriend might have COVID, so I won't sit close to you. Okay, moving on. We're 6 feet apart, trust me. Okay, so I don't have the whole hour to do this, but we had CH4 plus O2 goes to CO2 plus H2O. Seth knows what I was talking about. It was just a joke.
It's just 1, 2,
1, 2, 1, 2. Okay.
Could you double it and be the same?
Yep. 2, 4, 2, 4. Perfect.
It's just easier when you have to use
Okay. So we had done this before. So what was the total pressure? 2.86. Okay. The mass of water vapor in the flask at equilibrium. Do you remember how that came to be?
You put it through a prisoner and then times it by.
Okay, we use piv nert with that value, correct? All right, it has to be, yeah, you got to divide it by 760. And you use that to find N, and then you multiply it by 18 grams. Were we okay with that? What are you saying? Yeah, it's pretty different. But you die in both of them, so in the long run. Okay, letter D. Which reactant is in excess and how many grams of it remained at equilibrium? So which one was in excess? And how many grams?
0.234 or 235.
Grams? 3.754. 87 to be a little off. Just FYI, if your total mass of your reactants is 10, you better not have 87 made. Just saying. Total pressure of the flask at equilibrium is?
9.94.
What?
1.94 ATM.
Okay.
That's a minus the pressure. You minus the pressure for the water vapor.
Some of the water turned to liquid.
So you minus that from the total and it changes your pressure.
Okay, here we go. F. After the reaction, is there any liquid water remaining in the flask? Yes. If so, how many grams? If not, then why? Okay, so yes, there was, right? How do we know the total water produced?
How many moles there were?
Okay, so you take your limiting reactant and convert it to, you can do moles or grams, but I'm going to do grams. Okay, so my limiting reactant must have been oxygen, is that what we said, right?
Yeah.
So I had 5 grams of O2, 32 grams of O2, and you may have already skipped this step because you had it in moles already. I'm just writing it out the long way because I didn't do anything above. 1 mole of O2. From my balanced equation, what did I have in front of O2? A 2. What do I have in front of water? A 2, very convenient. And then for every 1 mole H2O, I had 18 grams, right?
Yeah.
Okay. What's this number equal to? 2.81 grams H2O produced. It's fine.
Would you give us like half a point if we're like a little bit off?
I'd give you full points if you were that little off. That's not, yeah, it's not that far off. Okay, now I went to grams because I already had right here, I had this. So follow my logic here. The liquid water is equal to the total water produced minus the H2O vapor. Does that logic make sense? So 2.81 minus the mass of the water vapor I found was 0.09 grams. And I get 2.72.
Oh, sure.
Okay. Kind of all right? Kind of okay? People behind me? Blaine? Yeah, I could tell he wasn't talking chemistry. Brown, good. Triplets? Good, okay. Everyone else behind me? Yeah, everyone's silent. Silent usually, let's be honest, silent means I'm so lost, I don't even know what to say right now.
This class? Yes. Or tired.
Or you're tired.
I think you should if I'm silent.
Can you go through about grams of
Which one? This?
Yeah.
All right, Seth has requested that I go and show how to do the grams of H2O again. So this goes back way to chapter 4. We first have to determine the limiting reactant, which was oxygen. Are you okay with that part?
Yes.
Okay, then I did a long picket fence. Most of you probably didn't do this because you already had moles of oxygen. So let's just take a time out for a second. And if you think, If you already have moles of oxygen, you already did this piece. And then in your head, many of you did this piece too, because I've been saying it for months now. If the coefficients are the same, then the moles are equal. So most of you probably just took the moles of O2 and knew it was the same. So you just multiplied it by 18, which is what got you 2.6 something?
Yeah, 2.7.
2.72. So it's a little bit different, but rounding and all that, it's going to be fine. I just did it the long way because early up above, I had not already done these calculations. Does that help, Seth? Okay. All right. This question is on the test. It is on the test.
Exactly like that?
Exactly like this. Number's going to change. Number's going to change. Maybe the temperatures like, but it's going to say this exact thing just with different numbers. All right. Let's look at another one that will be on the test, if you're okay with that. Okay. This is 100% on the test. An unknown gas has a mass of 158 grams. This gas was contained in a 1 liter flask at a pressure of 0.984 atm and a temperature of 50 degrees Celsius. What is the molar mass of the gas? If it's that, draw it. If it reacts with oxygen, E, balance it. F, what's the heat of combustion? This is wonderful because this is this chapter. This is chapter 3. This is chapter 9. This is chapter 4. This is chapter 4. And this is chapter 8. You see the beautifulness of this. Okay, give it a shot. There, I will give you equations on the test. I will tell you PV equals nRT. And I will also tell you that M equals dRT over P. Do you remember what M and D stands for there? All right, this is your molar mass and D is your density. Okay, so there you go. Now, if you're wondering, it didn't give me density. Yeah, it gave you a mass and a volume. So you bet your bottom dollar it did. What? That tomorrow it'll be there. Tomorrow, I love you. Tomorrow, you're only. No one's gonna back me up here. A day away. I just started too low. My bad. It's the cold. Did my phone just ring? That's a weird one. It doesn't usually sound that way. Hello. It's okay. Okay, sounds good. We made eye contact and she's leaving now. It might be. All right, the police are coming for, oh, she's gone. The what? No. Mass, molar mass is in grams. Like you're finding the big numbers here. How many have no idea what they're doing? Just one? Okay, in like 2 minutes, I'll start working from the top. Everyone else just keep on going. I'm going to use my You Guac My World soap. Thank you for this.
Wait, someone told me you tried to trade that.
It was going to be a pretty good trade. I don't remember, but I think it was caffeinated. Yeah. It was one green liquid for another one. Caitlin Warner. Family has a thing for avocados. Who doesn't? All right. Well, hello, Carly's iPhone. Here we go. Hey, it turns out glitter floats in Mountain Dew. Who would have known? Oh, okay.
You guys are all in the class.
Do you think it's toxic? Drinking glitter is not bad for you, right? All right, here we go. What? Are your legs sore at all today? Okay. Mission accomplished.
Thank you for that. It was really
All right, I've been recording this whole time. I apologize, people, that I wasted time, but you guys didn't want me to anyway, to pause it. So here we are. The molar mass of the gas. So poetic. Density is, are you ready? It is 1.56. Tell your partner how you know the density is 1.56. Because it's that many grams over 1 liter. Sorry, the density. I'm just plugging this equation in. Oh, hey.
Oh, don't like that equation.
It's 1.56 times 0.0821 times 298 plus 25 more 23. Yeah. 323. And that is divided by 0.984.
Why would you say 1?
I didn't. Okay. What did we get? 43.1.
Just 42.
All right. How are we feeling? Okay. In part B, there's 2 completely different ways you can use that, and either one is fine. So if it's 42 grams and 85.6% of it is C, if you want, you can figure out the mass of C. So take 42 and multiply by 85.6%. So multiply by 0.856. Anybody? Hopefully it's 36. Is it? That is 36. 35.9, which means I wrote this test better. Why is it nice that it's 36? Because that's a multiple of 12. Where's that coming from? The molar mass of carbon, right? So we know it's 36-ish, 35.9, whatever. The next step, you would just divide this by 12, and it equals what? 3. Which means my formula is C3. And I would put H. And what do you think I'm going to put? What was the molar mass? 42, and I've accounted for 36, right? So what's the difference? 6. Does this say it is a simple hydrocarbon? No. So it can have a double bond, and this one definitely does. If this goes back a ways, and it was right before I got sick, so you may not remember. When it said a simple hydrocarbon, then it would have been C3H8, because H would have been 2 times X plus 2. That may not make sense. Go ahead. Nope. It's fine, because then you got the 3, and then you took the excess and threw it on there. This just makes it more accurate and more like, oh, hey, I got it. This is for sure right. Okay. Letter C, then draw the structure. So C, 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 but only have 6 H's this time, right? I need 8, so I'm going to have a double bond, correct? And so then I'd go 1, 2, 3, 4, 5, 6. If you don't have enough H's, you have to form a double bond. Now, does it matter where the double bond is? No. So this could ask, does it have a resonance structure? And you'd say, yes, it does. It could ask the length of these bonds. And you'd say, if this was bond A and bond B, you'd say they're both around 1.5. 1.5 what? 1.5 bond lengths, whatever. Like, just, they're roughly the same because it'd be resonance. But we're not, that wasn't on here, so I'm just going to get rid of that for a minute. Okay. Oh, the hybridization of the central carbon atom. So that's just this one. How many electron domains? 3. So sp2. All right. Then, if it were reacted with oxygen, what type of reaction would this be? Combustion. Give the balance reaction. C3H6 plus oxygen goes to CO2 plus H2O. Balance it. 2, 6, 6, 12, 6, 18 divided by half. Yep, good. Then letter F is where no one got the answer right last test. So we better review that tomorrow, right? Who, are you okay with this style of problem? It's coming 100% at you.